Good morning. We're excited to provide those of you who have wanted to come and learn a little bit more about the process of VOCs and PAM monitoring. My name is Joe Palumbo, and I will be your presenter, and I'm joined today by Andreas Kianos, who will be at the controls helping answer any questions that you have during the presentation. Please let me begin by telling you a little bit about American Ecotech. Founded in 2002, American Ecotech has been serving both industrial and government customers throughout the United States. We have a full team of engineers that are both specialized in system integration as well as deployment, on-site operation and training, as well as remote maintenance and support. We specialize in deploying rack-mounted VOC analyzers designed for PAMs and fence line monitoring systems. All of the types of ambient air monitoring systems such as shelters, trailers, and all of the support infrastructure are also deployed for all ambient air monitoring systems. Now, VOCs means a lot of different things to different people. You can have a VOC system that is simple as monitoring both methane, non-methane, BTEX, C6, C12, up to a full PAM system, which would be going ahead and doing the full array of elements. Today, in today's webinar, we're going to learn about what PAMS really is, how to manage and maintain a GC pre-concentrator, some of the common mistakes that people make in setting up a calibration system, and getting data from your GC monitor. And normally we go ahead and ask a quick question, just kind of get a feel for who's out there and what their need is as far as learning a little bit more about VOCs. There's BTEX, as I said, PAMS, C6, C12, methane, non-methane, and total VOCs or other. Take a moment to look at those and see why you are here today and what you would like to learn more about. All right, we're going to start with a brief overview and a history of PAMS and what it means to the overall ambient air monitoring community. In the beginning, PAMS was monitored by a passive, labor-intensive system that utilized SumaCan. An average daily sample would be taken into the can, and the can would be sent off to a lab. It would happen to be a lower cost to produce these readings, but there was labor-intensive and needed manual intervention in order to get the sample processed. Over time, an auto GC was developed. This would take hourly data and allow you to take that data and produce it into a formatted database so that you could go back and refer to and have that data readily available. It is a higher cost, and it does take a higher skilled individual to run the instrument, but in the long run it is more efficient and can be a benefit to you and your organization. Here's another picture of the automated GC. It was developed to have, as we say, near real-time data collection, and is designed to use in ambient air monitoring stations. Here's a little brief history on how PAMS was started. Back in 1993, it was recognized that both VOCs and ozone were always a threat, but wanted to get some better ideas on how those elements and pollutants were being distributed across the community. One of the interesting studies that was utilized and brought in good data through the use of PAMS was in 1998. The EPA did commission a firm to use a PAM system to determine if there was a change in ambient VOCs as a result of the introduction of the reformulated gas in 1995. These results were positive by showing a reduction in benzene related to the reduction in the fuel due to that reformation. While PAM systems were being developed, the EPA was looking to find 3 classified areas, both serious, severe, and extreme. Those monitoring agencies were given the option to either take those samples by what we saw in the SumaCan or start to use an automated GC to collect those samples and either send them through the SumaCan laboratory or take that data and put it into a database and analyze it that way. Here's an explanation of how a typical PAMS system is set up and how it would be utilized in an area that might be affected. At the very bottom, you'll see different colored dots. Those will represent a different station and what that station is going to be monitoring. Bottom there in the left-hand corner is the upwind monitor. Then you have your monitors that are a little closer to where the populated area is, where you might have max emissions. There's an ozone monitor just out on the side of the perimeter, and also another downwind monitor as well. The principles of PAMS and what the EPA wants to accomplish are pretty simple. You want to know where non-attainment and attainment is being adhered to. They want to make sure that they're being effective as far as implementing plans when those elevated levels are met. They want to be able to take and track those emissions and keep a database of where the extreme areas may exist, and also go ahead and make appraisals on both the reduction of ozone, NOx, those different VCs, and so on. And once exposure is identified, what would they do to eliminate those risks and improve the ambient air? A typical PAMS system is going to consist of different components, and we're going to go over what a normal rack system would look like. First, you need a pre-concentrator. We're going to talk about what a pre-concentrator does here in the next set of slides, but for the time being, we're just going to go, like I said, what's going into the rack. Next, you're going to have a PID-GC, then an FID-GC. You're going to need gases in order to make sure, and you're going to be able to calibrate your system. So this manifold would be able to manage your gases and your calibration sources. A hydrogen generator for the FID, and finally a zero air generator to make sure that air is clean while it's being pushed through. Next, we're going to go ahead and go through what a pre-concentrator is and how it operates and how you would maintain it. The purpose of a pre-concentrator is to sample the ambient air and to get the most even and consistent sample. It helps in evening out the air when spikes may occur or other related air events. An example is that a spike of methane may happen within the hour, but as the air pushes through and mixes with the other air, it averages itself out for the entire hour. As you turn on your system, you're going to have to make sure that you go ahead and warm up, or let the GC warm up and to get ready to do what it's about to do. In that first hour, air is pulled through tube 2, the one on the bottom there, sending air just straight through. The air is not being analyzed, it's not being sampled. It's just an option that allows the air to flow through, while tube 1 is collecting the first sample to be analyzed. The air is heated up. It creates a sample, so that average is going to send through and have the analyzer do what it was meant to do. In the second hour, that tube that was collecting and just sending air right through the GC now closed itself up. And tube 1 that was collecting that air for that first hour is now opened up and sent to the GC for analyzation. In hour 3, the process has reversed itself, and now tube 2 is open because it was collecting for that previous hour and sending through and doing exactly what tube 1 was doing in hour 2. Now I'm going to pass the microphone over to Andres, and he's going to explain a little bit more in detail about the process I just went over.
Yeah, thank you, Joe. Well, what we got in here, we originally did the diagrams just really to give you a bit of an overview of simplified version of what the pre-concentrator does. And here we got actually a schematic of what the pre-concentrator has inside. What we can see there is we got tube A and tube B, and we got a trap that is capturing all these gases over the period of the hour that is being sampled, as we were describing before. So, for example, during the first section when the instrument is on standby, all we have going through the trap is just carrier gas, as we can actually see it over here. On the second one, what you can see then is we start collecting the sample. That sample gets collected on that tube A. So at the moment we're collecting sample in tube A, we got here is we're conditioning the sample for optimal absorption at the trap. Then that air that is being collected at the tube A is being dried, while at the same time now we're switching to that tube B. That's kind of that switching that Joyce was talking about. And when that is happening, we get transferring everything that was in tube A is being transferred into the trap, being prepared for collection. So now we're actually trapping this air into the trap there. Then we basically start the transfer onto the GC, the pre-absorbent and then to the GC. At the same time, all this time that I've been saying that's happening, we're collecting sample on the other one. That's what's been happening over that hour, and then that's actually off to the GC. So that's exactly the same process that we described before. We wanted to actually show it on a simplified version with just diagrams before coming into here into a more specific. So you want to just take over again and talk a little bit about calibration?
Okay. So the most important thing in making sure that your GC is going to give you the right readings is obviously with any other analyzer or gas analyzer, you're going to have to make sure that your calibration process is in place. As we were talking about the GC, you want to make sure that your system is warmed up before you go ahead and start to kick into the process. That can take anywhere from 30 minutes to an hour to warm up the system, get the pre-concentrator ready for samples. What you also want to do is make sure that you're matching up for what you're analyzing, making sure that your the proper gases are set up in that manifold and that you're making sure that those gases are there. Most calibrations can be done as a single point. And also, you want to make sure that you pay attention to your column efficiencies. Make sure that the columns are ready and that they are consistent every single time. Now we're going to go into talking about the difference between FID and PID and how that calibration process influences the proper readings that you're going to get from the analyzer. Andres, if you want to take over at this point.
Sure. Well, on an FID, what we have is the flame ionization detector. So obviously, when you're running an FID, you require some components such as your hydrogen generator, air to make sure that you have a flame ignited, and then that actually allows you to detect certain parameters and certain components. In the PAMS application specific that we've been talking about, we don't use a hydrogen bottle, we use a hydrogen generator because part of what the EPA suggested for the monitoring stations, the PAMS, was that they have to have be self-contained. They have to basically be able to run independently. So we didn't want to have hydrogen generator bottles. However, if your application doesn't require to meet a specific or very strict PAMS criteria, you may actually want to choose to use a hydrogen bottle. One of the advantages of using a hydrogen bottle is that it's pretty dry, and when you actually got air going through the columns on the separation of the gas chromatograph, what you're going to find is that the drier your carrier gas air is, the better. And then, yeah, you're going to use hydrogen as your carrier gas, then you probably want to make sure that that's very dry. Otherwise, you're going to start having troubles with the columns. Some of the parameters that you can measure with an FID, and what the question is why FIDs and PIDs, is kind of what we listed in here. So some things like your methanes are parameters that you wouldn't be able to detect with a PID, but that's what you need as FID. So the FID technology will be more sensitive towards those components. And then we also have the PID, which what we got here is a gas chromatograph of a PID sensor detector, and which the PID is a non-destructive sample, meaning the sample comes in and just basically gets charged with light, and the light is actually charging. It's a photoionization detector, so it gets charged with that light, and then the charges get released into the detector. So we're seeing here, however, we don't actually destroy the sample, unlike in the FID scenario, where the sample is literally burned. So with the PID, you detect all the different type of parameters, such as the one that you can actually see in here right now. So, is there anything?
No, once we've determined that we've utilized our system to what it was meant to do, obviously what the most important thing out of the machine is going to be the data that is produced. And now we're going to talk a little bit about what you can do to make sure that that data is stored, organized, and retrieved in its most efficient way.
Well, the one thing that's important to know and understand in here is the timing of your data. So we're all used to measuring meteorological parameters, even some of the oil gases, where the data that is being collected is literally in real time. So what you're actually reading right now on the screen of your analyzer is the data that you're collecting right now. Because we have a pre-concentrator specifically on PAMS application, then you're now starting to you have to understand that the data that you're actually coming out can be up to about 2 hours behind the hour that you're actually when that sample was collected. The first hour, that sample is going through the pre-concentrator, and within the second hour, that sample is being analyzed, and hence the number that is being produced comes out most likely basically on hour number 2 is a sample that was collected 2 hours ago or after 2 hours ago. Now, if you don't need a pre-concentrator, GCs on their own can actually give you things like 15-minute reading. So you can have within 15 minutes a reading just by running samples straight through the gas chromatograph. But so that you get fast response, but then you start to actually have problems with averaging. Why? Because let's say, for instance, you have a sample that you collected 15 minutes ago, and that particular sample happens to have a high reading. Well, that high reading is a representation of that 15-minute sample, but it's not a representation of the whole hour. That's why the pre-concentrators come in, and one of the functions of the pre-concentrator, as Joe was saying earlier, is really to average that over the hour, or average that sample over the hour, so that we can actually collect a reading that is representative of that complete hour period, rather than just a 15-minute sample that may or might not be representative of the hour. So that's just the one that is most important to understand here.
Okay. So now that we've learned pretty much what the pre-concentrator does, what that relationship between the pre-concentrator and the rest of the system is, what we're doing for calibration. Once we got that, obviously you want to have an understanding of how you're going to deploy your system out into the field. And one of the things that is useful is the fact that the system can be flexible and be put into different types of enclosures. You have two set enclosures, one larger than the other up on the top row. You have a mobile trailer down there in the bottom left-hand corner, and you can also deploy one of these into a true mobile system in a van configuration as well. We're about to wrap up here, but wanted to take a moment to let you know that there are a broad range of instruments and equipment that can be both utilized for the entire PAMS system, as well as the sensors that are included. Here's a list of some of the other equipment that American Ecotech both services and deploys. If you have any questions, feel free to contact us at any time. You can contact us through email. Visit us at our website at www.americanecotech.com, or give us a call, and we'd love to talk to you. Again, thank you again for your participation and listening today, and we look forward to hearing from you soon. Thanks.
Thank you.